Okay, in this video we're going to continue talking about types of spread and everything, but we're going to be talking about Chebyshev's inequality. Now, unlike the empirical rule, Chebyshev's inequality holds for any data set, whether it be approximately symmetric or whether it is skewed one way or the other. And what Chebyshev's inequality says is that the proportion of the data that will be within k standard deviations of the mean is at least, and what we have is 1 minus 1 over k squared. So when we're looking at this, if k is 2 for 2 standard deviations, in this case, we can figure out, approximately what proportion of the data will fall within 2 standard deviations, whether we're talking about symmetric data or skewed data. And so what we do is we take 1 minus 1 over k squared. So that's going to be 1 minus 1 over 2 squared. So that's 1 minus 1/4. So 1 minus 1/4 is going to be 3/4, or 75%. So at least 75% of the data will be within 2 standard deviations. Recall from the empirical rule, we said 95% will fall within 2 standard deviations. This just says at least 75%. So this is still adequate for those that are approximately symmetric. We can also do this figuring it if k was 3. So 3 standard deviations. We take 1 minus 1 over 3 squared. So that's 1 minus 1/9, which leaves us with 8/9, or 88.9% of our data. So at least 88.9% of the data will be within 3 standard deviations. Let's look at an example of how this would be used. So in this particular example, we're talking about prices of homes. The mean price of houses in a certain neighborhood is $50,000, and the standard deviation is 10,000. Find the price range for which at least 75% of the homes or houses will sell. Well, this doesn't tell me if this is approximately symmetric or not. So I cannot assume that it's symmetric and use the empirical rule. So instead, I have to use Chebyshev's inequality. Okay. So using Chebyshev's inequality, we're looking for 75%. Well, we know that 75% is 2 standard deviations from what we just showed on the previous slide. So we're looking at the data that will fall within 2 standard deviations of the mean. So if our mean is $50,000, we are going to subtract 2 standard deviations of $10,000. We're also going to take $50,000 and we will add 2 standard deviations of our $10,000. Just like we were doing previously to find out our values at the bottom of our histogram and everything, we're going to do it here as well. So on the lower end, we get $50,000 minus $20,000. So that's going to leave us with $30,000 for our lowest part of the range. Here we have $50,000 plus $20,000. So that's going to leave me with $70,000 on the upper end of the range. When we're talking about these, again, therefore at least We don't know exactly 75%, but at least 75% of all homes sell, let's see here, sold in the area. Let me redo that. So, sold in the area will have a price range from $30,000 to our $70,000. Okay? So that's if we want to look at 75% of our data and find out its range. Let's look at another example. And then this next example, we're going to be talking about travel allowances. So a survey of local companies found that the mean amount of travel allowance for couriers is 25 cents per mile. The standard deviation is 2 cents per mile. Using Chebyshev's inequality, find the minimum percentage of data values that will fall between 20 cents and 30 cents. So we know that we're going to be using Chebyshev's inequality. The problem is we don't know what K is, and we don't know what percentage. We're looking for the percentage. So what we're going to do is we're going to subtract the mean from the largest value. So our largest value is 30 cents. We're going to subtract our mean from that, 25 cents. We will get, there's a 5-cent difference. We want to know how many standard deviations this is. So we're going to take our 5 cents and divide it by our standard deviation of 2 cents. When we take 5 cents and divide it by 2 cents, we're going to get that this is 2.5 or 2.5 standard deviations away, which is not what we're exactly used to using, but it works. So our K is equal to 2.5 because that's how many standard deviations it is. Now, in order to get our percentage, remember we use the 1 minus 1 over K squared. So that's going to be 1 minus 1 over 2.5 squared. So I get 1 minus 1 over 6.25. So that's going to be 1 minus 0.16, which will leave me with a 0.84, or 84%. Remember, changing a decimal into percentage, we move the decimal over 2 places to the right. Hence, at least 84% of the data will fall between our two values given of 20 cents and 30 cents. Again, this is using Chebyshev's inequality because we do not know if it is approximately symmetric or not. Anytime we're unsure, we better use Chebyshev's inequality. So far, what we've been looking at are things that have the same units. Well, what if we want to compare things that are not the same units? In that case, we use the coefficient of variation. This coefficient of variation tells how large the standard deviation is relative to the mean. And so once we do this coefficient of variation, we can compare those spreads of data even if their units are different. So I can compare temperature to length of days, or I can compare money to scores, or anything of that nature. We denote coefficient of variation by CV. And so the formula for coefficient of variation is going to be the standard deviation divided by the mean. All we do, remember to take the standard deviation divided by your mean. Coefficient of variation will always be a number less than 1, so it should be between 0 and 1, somewhere around there. So let's look at an example of this, and we're going to talk about the sales of automobiles. The mean number of sales of cars over a 3-month period is 87, and the standard deviation is 5. The mean of the commissions is $5,225, and the standard deviation is $773. I want to compare the variations of these two. Well, I can't just compare their standard deviations because they're not the same units. And I also want to make sure that I'm on a level playing field. So I want to compare their coefficient of variation. And so first thing I'm going to do is I'm going to look at the sales. And the sales, first of all, looking back through here, we have a mean of 87 and a standard deviation of 5. So for my coefficient of variation, I'm going to take 5 and divide it by 87. So my coefficient of variation will be 0.057, or 57 thousandths. Usually, we tend to round to 3 decimal places for this. I'm going to do the same thing for my commissions. So my commissions has a mean of 5,225 and a standard deviation of 773. So the coefficient of variation is going to be 773 divided by the 5,225, in which I get 0.148, or 148 thousandths. And literally what we do is we look at which one's larger. Well, in this case, the commissions has a larger coefficient of variation. So since the coefficient of variation is larger for commissions, the commissions are more variable than the sales. And again, this is great for comparing things. Even if they are the same units, we want to make sure that we have the correct idea and are comparing two things that really should be compared. And so coefficient of variation has no units. It gets rid of your units, and it just has a value that we can actually compare. Try some problems using Chebyshev's theorem, Chebyshev's inequality and coefficient of variation. If you have questions, please let me know.